Welcome to tutorial 13, where we're going to be listening to oscillators. I'll explain how the circuit functions in great more detail later, but very quickly we have a switch that we need to press which will activate the circuit. That turns on a relaxation oscillator that we've used previously that produces an output frequency that's going to go to a 555 buffer that can then be used to drive this loudspeaker. If we connected the loudspeaker directly to this pin 3, the output of the oscillator, probably it would be extremely quiet if we could hear it at all. And we can change the frequency of the oscillator by using a variable resistor here. So this variable resistor is in series with this 220 ohm one. So let's have a look at how that circuit works. So in front of me, here is my circuit, here is my switch, here is my variable resistor and my loudspeaker and my two 555s. So I'm going to press the switch and hopefully you should hear the loudspeaker come on. And on the oscilloscope you can see the frequency of the output of the oscillator. Very quickly I'm going to show you the output of the buffer, only because you can see how messy and noisy that signal is and it's very difficult to measure. So I'm going to go back to the output of the oscillator to allow us to make more accurate measurements. Now, one other thing, we said there was a variable resistor. As I change that variable resistor, you can see the waveform get a lot closer together. So the time period has decreased and you can fit a lot more of those waveforms in on the time base that we're currently on. And down again. So you can have a little play with the frequency. Okay, so let's have a little look at the measurements in this activity. So the first thing to do here is to measure the minimum and the maximum frequencies from the output of our oscillator. So the minimum frequency, i.e. the lowest frequency, is the one where the waveforms are furthest apart. The maximum frequency is where we have the waveforms closest together. So we'll go back. There is our lowest frequency, and I'm going to measure the number of divisions, which is 1, 2, 3, 4, 5.4. Remember, it's the time low and high together. So our minimum is 5.4 divisions, and our time base setting is currently on 2 milliseconds per division. So, as in our previous practicals that you should be experienced at now, we have 5.4 divisions times 2 exponent minus 3 for milliseconds per division gives us 0.0108. Now you'll notice that doesn't show times 10 to the minus 3. That's because this answer is in seconds, so it's 0.01 seconds. You can still put this into milliseconds or seconds. Sorry, I'm going the wrong way there. There we go. So it's 10.8 milliseconds. And I'm going to do that just because we are used to working in those values. So it takes 10.8 milliseconds or 0.0108 of a second for one waveform. Let's measure the maximum. So I'm going to go right up. Quite a high pitch. And you can see that the waveforms are too close really to measure, so I'm going to change my time-based setting. There we go, and change the position so I can measure one waveform. And looking at this, I have 1, 2, 3, 4, 5, 5.7, 5.6 divisions. So with this example, it is 5.6 divisions, but each division is 0.1 of a millisecond. 0.1 of a millisecond. 0.1 of a millisecond. So that is 5.6 times 0.1 exponent minus 3 equals 5.6 to the minus 4, shift engineering, 0.56 milliseconds. 0.56 milliseconds. Okay, so let's work out what the frequency is of the maximum and minimum now. So 0.56 milliseconds, x to the minus 1, because 1 over time gives us frequency, equals 1785 hertz. 1785 hertz. Our other one was 10.8 exponent minus 3 milliseconds, and x to the minus 1 of that to give us frequency equals 92.59, so about 92 hertz. So what we're saying is that our waveform varied between 1785 and 92 hertz in this circuit. So we can work out our calculated frequencies to compare our theoretical and practical values. But we need to know something in this circuit. We need to know the value of the resistor and the value of the capacitors. Well, the capacitor in this case is 1 microfarad in both cases. So let's enter that into our sheet. 1 microfarad, 1 microfarad. But we have a variable resistor in this circuit that varies between 0 and 5,000 ohms. And in fact, it is a 4,700 ohm resistor, as it has written on it. So the maximum resistance is 4,700 and its minimum resistance would be 0. But it is in series with this 220 ohm resistor. Now the reason that this 220 ohm resistor is in the circuit is because otherwise, when the variable was set to 0, if we didn't have that, it would just be a short circuit from the output back to the input, and that would do harm to the circuit. So this 220 ohm resistor is just producing enough resistance to stop anything getting damaged. So the maximum resistance in this circuit is 4,700 plus 220 ohms, which is 4,920, and the minimum resistance is 220. Now, do we know which value of resistor would give us the maximum and minimum? So let's do a calculation. So we know that the frequency of this circuit is equal to 1 over 2 times C times R, where C is equal to 1 microfarad. So 1 over 2 times 1 microfarad times R. Well, let's work out the minimum value of resistance, which was 220 ohms first of all. So we have 2 times 1 exponent minus 6 is the capacitance, times 220 ohms equals 4.4 times 10 to the minus 4 And we'll do x to the minus 1 for that to give us the frequency equals 2272 Hertz. That's one value. Now we can assume that that's pretty much the maximum value, but we'll do the other value as well. 1 over 2 times C times R, where it's 2 times 1 microfarad times the resistor, which is now the 4700 plus 220, which gives us 4920 ohms. So 2 times 1 exponent minus 6 times the 4920, so I can put in 4.920 exponent 3, which is the same as 4920, equals, and then do my x to the minus 1 equals 101 Hertz. So obviously when we use the minimum value of resistor, it gives us the maximum frequency, and when we use the maximum value of resistance, it gives us the minimum frequency. So the two values there are when minimum value of resistor gives us maximum frequency, so minimum value was 220 ohms, and that gave us a calculated value of 2272 Hertz, and the maximum value was 4920 for the resistor, and that gave us a value of 101 Hertz. And how do those results compare to our measured values? Well, that's quite a way off here, but about 400 Hertz as a tolerance with our resistor capacitor is acceptable, and here we were pretty accurate. We were only 9 Hertz away. So let's have a look at how the circuit works. Okay, let's look in a bit more detail exactly how this circuit works. Now, firstly, why when we press the switch does it turn the circuit on, and why when we release the switch does it turn the circuit off? Well, this takes us back to the astable circuit we did last that looks at pin 4, and pin 4 is our reset pin. So normally pin 4 is held high. That way the circuit would just work. But in this case what we've done, we've held pin 4 low by this pull down resistor, the 2.2k ohm one. So pin 4 is held low because it's connected directly to ground via a resistor. But in this circuit now we have this switch, and when we press this switch it connects pin 4 directly to 5 volts. And when it does that, this 2.2k ohm resistor becomes irrelevant because the path of least resistance is via a switch which has no resistance up to 5 volts. And when we press the switch, pin 4 is held high and the circuit will work. When we release the switch, the 2.2k ohm resistor comes into play, holding pin 4 low. We can see that happening. And we can do that using the oscilloscope rather than a voltmeter. So if I connect my oscilloscope to pin 4, at the moment you can see that this is set at 0 volts. If I just put that on the ground, you can see the line is in the middle. So therefore DC must be 0. As soon as I press my switch, go, you can see that pin 4 goes high. It's risen 2.5 divisions, with each division worth 2 volts, which means it's gone to 5 volts, 2.5 times 2. When I release it, it drops back down to 0. Press, and each time you can hear the loudspeaker coming on and going off as to whether that switch is pressed. Going back to my circuit. So this is my input part of the circuit, the switch. The output part of the circuit is my loudspeaker. Therefore, everything else in this circuit must be what we call the control portion. So there's quite a lot there. We have the input, we have the output, and we have the control. And the control contains two elements, of course. One is our oscillator, our relaxation oscillator, where we can vary the frequency by changing the value of the variable resistor. And we have this inverting IC buffer, which is used to drive the loudspeaker. The frequency at the output of this pin and the frequency at the output of this pin are identical in terms of frequency, not necessarily in terms of shape, because the shape of this, as we saw before, is rather ugly and messy because the loudspeaker is trying to draw current from the circuit, and therefore it is distorting the output of that pin 3 buffer. If we remember, the IC buffer is an inverting buffer. So what we're saying is that when the output from this pin 3 is high, the input to this pin, this 555 buffer, is also high, which means the output of this pin 3 must be low. And when this output is low, because the loudspeaker is connected high, then the loudspeaker is on. When this here is low, this here is low, which means that this output will be high, and therefore this loudspeaker will be off. The fact that this is going high, low, high, low, high, low, and this is therefore going low, high, low, high, low, high, means we are still hearing this frequency at this output. Moving very briefly onto the block diagram, which is the first time that you will have seen a block diagram, also known as a system diagram. We always start with our input, our output and our control feeding into one another, and we can then separate the blocks out. In this case, our input was our on-off switch, our output was our loudspeaker, and our control is our relaxation oscillator and our buffer. Finally, just having a little look at the results. Generally, what did you notice about the mark space ratio of the waveform? Well, if we just go back to our waveform, I'm going to just increase the frequency again. Sorry, I need to connect that back up. You can quite clearly see that the mark is much longer than the space, probably a ratio of about 3:1. And as the pitch gets higher or lower, what happened to the oscilloscope trace? Well, as we've stated before, as the pitch gets higher, the frequency gets smaller and we get more of the waveforms on a screen. And as the frequency gets lower, the time period extends and therefore it gets longer. End of activity 1. In activity 2, we are going to build a light to sound converter. So in other words, light is going to be our input and sound is going to be the output, and I would like you to produce a sound whose pitch increases as the light intensity increases. Okay, so as the light increases, the pitch increases, or the frequency increases. Now if we go back to our original circuit diagram, we can see just enlarge that, we can see that the components that changed the frequency were the capacitor and this little arrangement of resistors. Light devices, where we have a change in output as light falls on something, the only component that we have met that does this is called the LDR, the light dependent resistor. Therefore, it makes sense that we can replace our resistance in this circuit with an LDR. We can't replace the capacitor. This resistor here, the 220, was only needed to stop the problems associated with turning the variable resistor down to 0. So in fact now we know that a light dependent resistor doesn't go right down to 0 because it would require very, very, very intense bright light to do that. So we can replace the 220 ohm resistor and the 5k resistor with our LDR. So if we take both these components out of the circuit and put the LDR in from pin 3 back to our pin 2, pin 6, that should do the job. So I have here the circuit that I've already built. Here is my LDR. Once again, I'm going to press the switch and listen to what happens. And as I cover the LDR, and that is with the paper right over the top of the LDR, giving it its maximum resistance, and with the paper off, its minimum resistance, i.e. as we have more light, we are increasing frequency. As we reduce the light, we decrease the frequency. We can actually have a little bit of fun because, of course, we can, if we increase the light more, we will increase the frequency. But my office is quite dark, and I needed it to be so that we could see the oscilloscope traces. So I need to produce some additional light. And I could do that by using a light bulb. So if I connect up my light bulb into a circuit, there we go. And now you can definitely hear that that pitch is higher. And as I bring the light bulb closer, so very high range of frequencies. I'm not even sure that would be audible on a video. All that's left to do in this activity is to complete our circuit diagrams and our block diagrams. So on our block diagram, our input is still our on-off switch, our control is still our oscillator, but we can add an additional block in here to do with light detection. So find a way of adding our block in. Our buffer is still in our circuit and our loudspeaker is still in our circuit. Our circuit diagram is pretty much the same, apart from we've removed the two resistors and put an LDR in their place. This is the end of activity 2.